Hello everyone, welcome to this video. In this video, we'll be talking about more results on finite groups. So we'll be proving these results later on in the course. For the time being, because we were studying about various finite groups, so let's also bring into your notice all these results, right? So let's start with the first result. Here it tells us that the order of a subgroup divides the order of the group. Now this is a quite important statement here. The order of the subgroup divides the order of the group, right? The next statement is for a finite group, the finite group need not have exactly one subgroup. We know by the fundamental theorem on finite cyclic groups that every divisor of the order of the group is has exactly one subgroup. But if we remove this condition of cyclic from it, then for only the finite groups we cannot say the theorem holds in that case also. So therefore a finite group, they need not have exactly one subgroup corresponding to each divisor of the order of the group. For example, for some divisors there may be the case that we have no subgroup, and for some divisors there may be the case that we have many divisors, right? For example, if we consider the dihedral group, the group consisting of the symmetries of the square which has order 8, right? Its elements, they are of this form: R0, R90, R180 and R270, right? Then we have H, V, D and D dash. So corresponding to this dihedral group D4, right, this has 5 subgroups of order 2 and 3 subgroups of order 4. So this does not follow the property which is given by the fundamental theorem of on cyclic finite groups. Why? Because in this case the group that is not cyclic in nature, so therefore the result does not follow the given theorem, right? Let's move forward and see our last result here. Although cyclic groups, they constitute a very narrow class of finite groups, right? They play a role of building blocks for all finite abelian groups. So that means they act as, cyclic groups act as building blocks for all finite abelian groups in which all the elements, they commute with each other, right? Finite means they would have finite number of elements within it, the order is a finite number, right? So cyclic groups, they form all the finite abelian groups, just as primes are the building blocks for integers and chemical elements, they are the building blocks for chemical compounds. In a similar way, you can say cyclic groups are the building blocks of finite abelian groups. So for the proof of all these results, we'll be doing it later in the course. So that is it for this video. Thank you for watching.